Hi, welcome back to Structural Analysis Made Fun and Easy. So this is Pre-Stressed Concrete Design, second edition by M.K. Hurst. I'm looking at chapter 1, and this is problem number 1.7. So it says, a pre-stressed masonry retaining wall is shown in figure 1.39, comprising a hollow box filled with mortar to ensure a composite section. The section properties are section modulus Z equals 6.67 times 10 to the power of 6 millimeters to the power of 3 per meter. Cross-sectional area A equals 2 times 10 to the 5 millimeters squared per meter. If the pre-stress force is 700 kilonewton per meter applied through the centroid of the wall, determine the maximum height of the retaining wall H, such that the joint between the wall and the base is just put into tension. Assume the soil gamma equals 18 kilonewton per meter cubed, and phi, that's the angle of shearing resistance, isn't it, equals 35. So this would indicate that this is a granular soil behind the wall, not a clay. And ignore passive resistance in front of the wall. Here's the picture of the wall. So the height of the material behind the wall is H, and it doesn't show a section through the wall, but it's got a bar. So you've got 2 leaves of masonry, then it looks like an internal cavity filled with cement or concrete, and then with the foundation, then with the tensioning, it looks like a post tensioning bar, and that is 700 kilonewtons per meter. So let's get straight onto it. So this is the solution. Sorry about this, I just got a presentation, but refer to the picture of the wall in the textbook. So here's my drawing of the wall. So here's the ground level, H equals 0, and then H equals D. This is the active side, this is the passive side. And then this is the pressure, triangular distribution of pressure. P0 equals 0. Fa is the force from the active pressure, and then PD is the pressure at the depth of the wall to be confirmed, and then that Fa acts at 1/3 of H. Diagram of earth pressure behind the wall I got on this side. And then, so the question is, as stated, determine the maximum height of the wall such that the joint between the wall and the base is just put into tension. So that's page 1. 700 kilonewton meters is applied through the centroid of the wall. There is no pre-stress and eccentricity. So this is the bending moment diagram. M bending moment behind stem of wall. H equals 0. And then we've got stem of the wall, H equals D. Then there's a moment which is clockwise. So that is a minus moment. The tension, so what that does in the stem, that's tension on the left and compression on the right. Tension M, so the overturning moment is M. Sigma T is a tension moment, which is equal but opposite to sigma C, which is compression. Stress distribution in the stem of the wall. The useful essential equation is sigma T equals N divided by A minus M over Z, because there's no eccentricity, and that must be just equal to 0, because it says in the question just equal to 0. Sigma T must be just equal to 0 as tension just begins to develop on the inside face of the wall stem. So here we got N equals pre-stress force. M overturning moment from retained material pressure on wall. Overturning moment from retained material pressure on wall stem. A equals area of wall section. Z equals section modulus of wall section. Given A equals 2 times 10 to the power of 5 millimeters squared per meter. Z equals 6.67 times 10 to the power of 6 millimeters cubed per meter. Here's say the section of the wall is like this, but it's not It might not be. It says it's a hollow wall, but it doesn't show, but I'm just guessing. It's just for the sake of having a rough idea of what it looks like. So you might have 2 like hollow cavities per meter, or you might have 3 or 4. You might have 2 bars per meter, you might have 5. Just depends on but the N applied pre-stress it or post-tension is 700 kilonewton per meter. So that means in the equation 1, N over A equals 700 times 10 to the power of 3 divided by 2 times 10 to the power of 5 kilonewton per meter times 1,000 millimeter squared per meter. So sigma N equals 700,000 divided by 200,000 equals 3.5 newtons per millimeter squared. Insert this into equation 1. That means N over A is 3.5 minus M over Z must be equal to or greater than 0. That must mean that M over Z is equal to or less than 3.5 newton per millimeter squared. M is equal to or less than 3.5 times Z of the section, because M over Z must be equal to or greater than 3.5. So therefore M is equal to or less than 3.5 times 6.67 times 10 to the power of 6. But M so M 3.5 times 6.67 times 10 to the power of 6 is 23.345000. 23.345 kilonewton meter per meter. So it's, I'll write that again. Moment must be equal to or less than 3.5 newtons per millimeter squared times 6.67 times 10 to the power of 6 millimeter cubed. So that is 23.345,000 Newton millimeters per meter. So if you divide, oh yeah, so that's correct, 23.345. Oh yeah, 000 Newton millimeters per meter. So to get that into kilonewtons per kilonewton meter, you've got to divide by 1,000 from newtons to kilonewtons and 1,000 again from millimeters into meters. That gives you 23.345 kilonewton meter per meter. The maximum moment must not exceed 23.345 kilonewton meter per meter. So that's based on the allowable stress. This is based on the allowable stress. This is based on the maximum allowable stress based on the pre-stressing, and that will resist the moment and the area and the Z of the section. So now we've got to find out what the moment applied is at different heights of the wall. So the material, here's the diagram of the wall. So let's say H equals D. Material data, phi equals 35. Gamma unit weight is 18 kilonewton per meter cube. H of the wall, H equals D. And then FH is at 1/3. And FH equals half times P times pressure at H times H. Sorry, so I'll start this again. So let's start this again. The material data for this granular material behind the wall, phi equals 35 degrees. That's the angle of shear resistance. And the bulk unit weight is 18 kilonewton per meter squared. So let's say instead of calling it H, the height of the wall, I call H equals D. So the pressure at the top of the wall is 0. And then the pressure at the depth of the wall, that is equal to phi. Oh no, sorry, it should be pressure at the highest point, the pressure at the lowest point behind the wall is equal to Ka, which is based on phi, times the unit weight times D. Instead of calling it H, I'm going to call it D. So pressure at the depth of the wall, say it again, equals Ka active times unit weight times D. That means that FA and FH, the force from the pressure, that is the area of the triangular pressure. So the area of a triangular pressure is half base times height. FH equals half times PH times H. Because, oh, sorry, it should be PD, but PH and PD the same. And then the moment is FH times 1/3 of the height. So from first principles, if you want to look at my videos on soil mechanics, Ka equals 1 minus sine phi divided by 1 plus sine phi equals 1 minus 0.574 divided by 1 plus 0.574 equals 0.271. Therefore, phi d, the pressure at depth, which is pressure D, which is the same as pressure H, equals, as I said, Ka times gamma weight times H max, 0.271 times 18 times H max. FH max equals half times PH max times H max. I hope I'm not confusing you guys by just in all these videos, H equals D. I should have put D all the way through it, but it doesn't really matter because all you need to remember is H is the same as D, so it doesn't really matter. The moment is H max divided by 3 times F max. So what we're doing here is we're working out what moment we get from different height based on the height of the wall, and then the height of the wall, the moment from the wall must not exceed the value that I worked out in the previous video. So M, as I said on the other pages, M equals, oops, sorry, I'm going to do this. M equals H max divided by 3, which is, so M equals H max over 3 times the force. And the force is half times pressure times H max. And the pressure is Ka times 18 times H max. So that means that at the moment from the wall is 0.271 times 18 times H max to the power of 3 divided by 6. 3 times 2 is 6. That equals to 0.271 times 3 times H max to the power of 3. We know that the maximum allowable pressure behind the wall, for the properties of the wall that we have, the maximum moment is 23.345 kilonewton meters per meter. Sorry, that's wrong. So then H max to the power of 3 equals 23.345 divided by 3 divided by 0.271 equals, so if you keep those units, what I've done, I'm going to keep those units in kilonewtons and meters. So H max to the power of 3 is 23.345 kilonewton meters per meter run divided by 0.71 times 3. So therefore, H max to the power of 3 is 28.7146371463171. So H max is the cubic root of 28.7143637 equals 3.0622. So the max height allowable equals 3.062 meters. Oh yeah, so the maximum height of the wall is 3.062 meters for the pre-stress allowable. And that is the solution, which I checked in the book, which is correct. So I'll upload the notes this time. I scan it in and upload the notes. I'm hoping to redo this video. Then hopefully you can, could you please like the video? Please leave any comments in. Please download the notes if you want. It's going to be a new feature. You can take the notes, and then if it helps, work through the notes, and then you go through the video with the notes, and you can see all the workings. And then please can you subscribe to the channel, because then I could do more videos and improve the presentation. Obviously I need to improve my presentation and then improve the videos and then do more solutions for you guys. I think there's exams coming up, isn't there? There's exams coming up this for June, and the summer exams are coming, so If you want, if you guys need any help with your exams, please drop me a line as well. Thanks for watching. Hope you enjoyed the video. See you in the next video. Thanks.